everybody. Today I'm pleased to give a talk about the design of columns reinforced foundation based on column software. The outline of this presentation is first an introduction to define what is a column reinforced foundation, CRF, which are the benefits and the methods of column installation and also the associated type of soils. Then we move to detail the novel methodology for the design, and we will show the added value and its implementation by using column software. Then we will go through the validation of the results by a Tunisian case study for which we'll interpret the results, and then an assessment using numerical prediction or compared to column software predictions, and finally conclusion and recommendation. So a column reinforced foundation, it is an improvement of in-situ soils. Those soils are weak and or highly compressible, which exist mainly in coastal areas. As examples, soft clays for which the Young modulus is less than 3 MPa and an embryo cohesion less than 30 kPa, or loose sands, mainly saturated loose sands for which the friction angle is less than 30 degrees or the SPT less than 10. So what is about the reinforcement? It is an added material with enhanced stiffness and shear strength. Or it can be the treatment of the existing soil by adding a bender like cement, lime, or the combination of two. And the benefits of this reinforcement is to increase the bearing capacity of the reinforced soil and the settlement reduction, and also the acceleration of consolidation and the prevention of liquefaction. We will talk about columns installation by focusing on two cases, two types, the vibrocompaction and stone columns. As we can see here in this grain size diagram, so we can see for the zone where we have granular soil like gravel and sands. So mostly we do vibrocompaction. And if you're in the range of silts and clays, stone columns are much appropriate. But for the illustration, we here can see which are the steps for the installation of stone columns by the wet method. So we have a vibrator which penetrates the soil up to the reached depth of the column, and then we have the insertion of the added materials. As we can see, it's gravel, it's a granular material, and the vibrator, when we have the granular material here, this granular material will be expanded laterally. So if we can compare the diameter of the hole where we have the vibrator and the diameter of the installed columns, there is a big difference. So we do this reinforcement step by step, and as such the stone column is installed up to the ground surface. So we have to focus on the expansion of the initial soil, adding to the column. So this expansion induces also an improvement of the soil. It's like a consolidation. So for the two other practiced method, deep mixing and sand compaction pile can be also used as column reinforcement. What is about the novel methodology of design and the modeling of CRF? So the geometry consists in showing the soil profile the loaded area and the columns in 3D modeling. So here we have the loading foundation, and at the surface of the soil which will be reinforced, we put generally a drained layer, and then we have the columns under the area of the loaded foundation. So the columns of length HC is not necessarily end bearing. That means the length of the columns reach the depths of the rigid stratum. The columns can be floating, and as such, the length of the columns is less than the depth of the stratum. So, to talk about the design, we have the total area of the foundation, which is A, and the total cross section of all columns, it is AC. And from these two area, we will get the improvement area ratio, which is the ratio of AC, total column cross sections, divided by the loaded area of the foundation, and this is the Q parameter for the design. So the design of a CRF needs two verifications for the stability of the foundation. First, bearing capacity is the first requirement, and second is the settlement. And as such, we will show how we can get an optimized improvement area ratio. So when determining this optimized area ratio, we can move to the study of the behavior of a column reinforced foundation. As example, we can do experiments in laboratory, for example, using scale test models, or doing loading in situ tests or full scale tests. We can also do or implement numerical studies, investigation, for example, using the finite element codes, and we can move to the recommendation of the foundation. So, for the design, first, the constituents of the reinforced soil are assumed homogeneous and isotropic. We have the initial soil and the column materials. To deal with the bearing capacity, we have to introduce the cohesion and the friction of the initial soil. And we have to introduce the cohesion of the column material CC and its friction angle. These are failure characteristics. For the settlement, so we have to use the Young modulus and the Poisson ratio of the soil, and the Young modulus of the column, which is necessarily greater than the one of the initial soil, since it is reinforcement, and the Poisson ratio. So we assume a linear elastic behavior of the two materials. So after the investigation by Wasida and Carter in 2014, the optimized improvement area ratio is determined in two steps. When considering just an admissible bearing capacity of the CRF, for example, factor of safety just 1.3, so we can determine the minimum improvement area ratio. And when performing the settlement verification, we will determine the maximum value of the improvement area ratio, which means that the optimized value of the improvement area ratio is in between the minimum and the maximum improvement area ratio, combining the two verifications of bearing capacity and settlements. So first, it is well-targeted value because it is associated to the settlements of the reinforced soil. This settlements, we'll focus on that, is almost resolved at the end of construction of the building of the project. And since the columns are made up of granular materials, they behave like vertical drain. So the crucial issue for the reinforcement by columns when we have the floating columns. So here we have the settlement of unreinforced layer, which are under the columns. So it can happen especially for high compressible soils, and also the evolution of the settlement in time is, a problem for which we have to focus on. The optimized methodology is implemented as such. So this optimization, as we introduce first the bearing capacity prediction, we get the minimum improvement area ratio. The settlement prediction, when getting that the allowable settlements of the foundation is equal to the settlement of reinforced soil, we will get the maximum improvement area ratio. So how implementing this optimization? So we will increment for different steps from the minimum value of improvement area ratio to the maximum value by increment of this improvement area ratio, which is delta eta I. So, and for each steps, we will compute the total settlement, and for which we have to deal with several values of the eta incorporated. We call it incorporated because it varies from the minimum to the maximum value. And as we can see here, we consider those contribution about the settlement of reinforced soil. Wasidai 2003, Balam and Booker 1981, Shaw 1996, the French method 2005, and Brooms 1972. So, and for each steps, we have to check if the settlements corresponding to this eta incorporated I is allowable or not. So if not, what does it mean? It means that the settlement for this eta incorporated is greater than the allowable settlement. So it means it's not stable. Then we have to go to 3 and we increase the value of eta incorporated I with a new value. If the settlement complies to allowable settlements, that means the settlement, the total settlements is equal or less than the allowable settlements, so the optimized value corresponds to this value. And as such, we will get the output thus of the optimized area ratio. So for the purpose of illustration, summarizing that the new methodology of design has some added value. So we determine a minimum value of the improvement error ratio and a maximum improvement error ratio by the verification of bearing capacity and settlements. And the optimized error ratio means that we have a cost-effective design. So this methodology was embodied by Boissida and Hazard in column software, and the settlement of reinforced soil is a shortened settlement because the column materials, its permeability is high and there's an acceleration of the consolidation settlement. And for more details, we can, check this reference and to see how we implement different case study by this methodology. And we can also learn or understand that there is a relationship between the columns dense and the allowable settlement of reinforced soil. So interesting notice that this methodology applies for all types of reinforcement by columns. That means valid for stone columns, deep soil mixing, sand compaction pile. So now for the illustration, consider this Tunisian case study, which is an oil tank of diameter 54 meter diameter, and it associated to an applied assumed uniform stress at the surface of the soil about 120 kPa, for which we verify that it is greater than the admissible bearing capacity of the soil. And here we have the properties of the geotechnical parameter of the initial soil are 3.6 megapascal for Young modulus and just 25 kPa for the unbrained cohesion. So when we designed and reinforced by stone columns, usually we can consider young modulus of the columns 10 times of the modulus of the soil, that is 30 MPa, and a friction angle with a high value, for example 42 degrees. And then for this case study, implementing column software, we identified that we need a minimum of improvement ratio equal 30% to get the value of 120 kPa of the bearing capacity of the reinforced soil. But this value is not enough for the settlement of the reinforced soil. And then we predict that the optimized improvement error ratio, we will show the details, it is exactly 30.64%. Meanwhile, the executed reinforcement was with value of 35%. That means it is greater. And the number of columns, stone columns, was 708 columns and of diameter 1.2 meter. So here we have an illustration of one of the output of column software, which is the apparent Young modulus, which is identified by this equation. The value of the apparent Young modulus, it is correspond to what we call the law of mixture. It is eta EC, here we have EC plus 1 minus eta ES. So from this equation, we can see that the Young modulus of the apparent Young modulus of the reinforced soil is inversely proportional to the settlement. So when this ratio is, for example, the show method is here, for which zero horizontal displacement, so we have a settlement less than the method, for example, by Borsida and all, for which the apparent modulus is lesser. And then we can compare the 4 methods I talked about, French standard, Balam and Booker, Shaw and Borsida and all. And we can see here that when we consider zero horizontal displacement, it's like the odometer model. So the settlement is at minimum and the apparent modulus is the biggest. And then the methodology we are suggesting is on the conservative side because it considers the lowest Young modulus of the apparent Young modulus of the reinforced soil. So here we have exactly the details. The applied stress is 120 kPa. Using limit analysis, to call it lower bound of immunization method, we get 160 kPa as mean failure value, and the French standard is very different, more than 500, simply because here you are using 3D model, but here we are just using what we call the isolated column model. So we consider only the columns. So for the settlement at the tank axis, the recorded value for this Tunisian case study was about 4 centimeters. And for the method we are considering in the software, almost we are in between 4.2 Shaw method because we assume no horizontal displacement, and 5.8 by Borsida and all method, but they are comparable. But the well-known Preeb's method, considering 2 assumptions, the settlement can be either 6.1 or 23 centimeters. So for the execution, we consider 35%, and column software using this novel methodology, the optimized reinforcement is 30.64. So we can see that we have a saving of added material which is about 10%. So going to the numerical prediction, we performed with FLAC 3D for this oil tank, a 3D model which is like a parallelepiped of length the whole diameter of the reservoir is 54 meter, and just breadth of about 2 meter, and of course the depth, because the columns are unbearing, of 7 meters. And the maximum settlement for the unreinforced soil is 23 centimeters. And then when we consider the reinforcement of this 3D model with columns and bearing columns that we can see here, okay, and the results I'm showing here exist in this publication, and the prediction method you can see on this table. For the settlement, the reinforced soil settled just 5.2 centimeters, using FLAC 3D code. So when we compare 5.2 to 23, we have of about 1/4. That means we have a significant reduction of settlement. Whilst by the method, by Bosida and all, the results of prediction settlement of reinforced soil is very similar with FLAC 3D, and as for the settlement of the reinforced soil, it's 5.8. The verification, the settlement of reinforced soil by French method and Balam-Lecourt are comparable, but as we can see, the settlement of unreinforced soil, because this one uses the isolated column model and this one uses the unit cell model, we have quite different prediction. So to conclude, we introduce a general methodology of design of foundation on soil reinforced by end-bearing columns, for which we can get an optimized improvement area ratio. This methodology was implemented in the columns 1.0 software, and the prediction by this software were assessed by numerical prediction FLAC 3D. So in the conclusion, we in brief just give some illustration of the output of the software columns. So on the first output sheet, we have the characteristics of the foundation, the geometry, applied stress, and the characteristics of columns, and then the initial soil in case it is composed by several layers. For each layer, we have to introduce thickness, unit weight, the friction angle, the cohesion, Young modulus, and Poisson ratio, and either the permeability. So here we have a sheet which gives us the minimum improvement area ratio. In this case is 0, which means we don't need to reinforce for increasing the bearing capacity. It can happen. And here we have the optimized value, which is equal to the maximum improvement area ratio. And the software can deliver, of course, as a function of the spacing, different diameter of the columns, and we can see that the volume of incorporated material is mostly the same. And we have also the settlement of unreinforced soil. In this case, it is about 40 something centimeters, which is inadmissible, and the settlement of reinforced soil, which is about of 80 centimeters, because it is, a very big tank and associated to several layer, compressible layers. So the admissible settlement was considered to be about 80 centimeters. So about column software, copyright is by Simpro Tunisia, and in this table we have the institution purchased the software from several countries: Egypt, USA, Tunisia, France, Senegal, USA, Egypt, UK, and experienced project by Simpro company, for example, Benin, Tunisia, Algeria, Tunisia, and training session of the software took place since 2010 in South Africa, then Australia, Tunisia, Vietnam, Tunisia twice, and the institution by students. Column software was delivered to students preparing their graduation of project or PhD sometimes, of Tunisia, Algeria, Morocco, Mozambique, Algeria. And Finally, just an information, all the details about design of column reinforcement can be found in this book. And thank you very much for your attention.